Hello, today we will have our last lecture about electromagnetism, and in this lecture we will talk about magnetism, and so this will be about magnetism and electromagnetic induction. So this will be electromagnetism. Lecture number 3. So it will be through electromagnetism, because we will be dealing with electric and also magnetic phenomena. So magnetism we will be dealing first. So magnetic effects are more easily visualized, because magnetic effects are stronger than electric effects, and magnetic fields, they are associated with currents. So magnetic fields associated with currents, and if there is electric current, so basically what is current? Electric current, it is moving charged particle. So if we have moving charged particle, it can be moving proton, it can be moving electron, any charged particle. Can be positive sodium ion. Any charged particle that is moving, it is creating magnetic field. Also it can be motion of if current is flowing through the wire, we have the current, so then we have magnetic field, because electrons are moving in the wire. As we remember, yes, electrons are moving in the wire. So electrons, I shown them outside the wire, but electrons are moving inside this wire, and so moving charged particle creates magnetic field. So permanent magnets, they are magnetic. So bare magnet, North Pole, South Pole, so they are magnetic because of the currents that are at the atomic level. So from permanent magnet or a bare magnet that we know, it was known even in the ancient times that magnetit, the formula is 3 atoms of iron, chemical formula 3 atoms of iron and 4 atoms of oxygen. It is natural magnetic material, and this magnet, it can be, bare magnets can be made of magnetic materials such as magnetit. There are other magnetic materials we will like neodymium magnets, like other metals can be magnetized to make bare magnets. So just speaking about bare magnet, magnets always has north and south pole. So south pole is sometimes can be visualized in red color, and north pole can be visualized in blue color. And we can show that magnetic lines go from magnetic field, so they go from north pole to the south pole. So these should be symmetrical lines, so they go from north pole to the south pole. And this is magnetic field created of the bare magnets. So bare magnet, it creates magnetic field in the space. So this magnetic field, as we had the electric field strength, the strength of magnetic field is called as B vector, so it is called magnetic induction. So it is the strength of the magnetic field is called magnetic induction historically. So magnetic induction, and these arrows of these lines going from north to south, they were chosen because how small magnetized ferrum particle reacts to this magnetic field. So if you put small magnetized particle of iron, ferrum I said, sorry, of iron, this small magnetized particle of iron would behave like this. So it would position like this in the magnetic field. If you position it here, so the lines we can draw like this. If you position it somewhere in somewhere else, so if you position it here, so it would be orientated like this. So S part, south part, and south pole and north pole. So always magnets have two poles. There can be magnetic monopoles. So similar poles of two magnets, they repel each other. Different poles, they attract each other. So so small iron particles are aligned in the field according to these lines. You see, this direction is chosen to this blue, how this blue pole of magnetized iron particle is aligned in the field. So here it would be aligned in the direction of also of these lines, of these arrows. So it would be like this. This is red is aligned to the blue, and this blue is aligned to this red. So it's always like this. The magnetic properties of the material, as I told you, they arise from the motion of electrons. So magnetic properties of materials, they come from electric currents, as I said. So electric current is basically inside some kind of material. It is the motion of electrons. So electron, they have two types of motion. So electrons move in orbits around nucleus, and electrons spin around their own axis. So electrons spin or move, we can say. So electrons move in orbits around nucleus, and electrons spin around their own axis. So like Earth is moving around its own axis, spinning. So this spin of electrons around their own axis is responsible for the most part of the magnetic properties. So electron spinning around its own axis, so it's spinning, so it is producing magnetic field. Is like little magnet. So electron is like a little magnet. If there are two electrons spinning in one electron is spinning in one direction, another electron is spinning in different direction, so these magnetic properties, they cancel out. So if there are unbalanced spinning electrons to some kind of direction, the material has magnetic properties. So most of the materials are non-magnetic because electrons are balanced. The spinning of electrons is balanced, but those. So as we know, conductors, copper, aluminum, and non-conductors. So these are conductors, but all of these, they are non-magnetic. On the other case, iron, nickel, cobalt are magnetic. So if so iron, it has 4 unbalanced electrons. So in iron there are 4 unbalanced electrons, 4 unbalanced spins of electrons. So iron, basically a piece of iron is neutral, is magnetically neutral, because there are domains of these magnetic domains in the piece of iron that are randomly distributed. So we can show that these domains are positioned randomly, so they balance each other. But if iron is positioned in magnetic field, so this is unmagnetized. Unmagnetized iron domains are randomly distributed. So, but if iron is positioned in external magnetic field, so iron is magnetized. So magnetized iron and magnetized iron, these in domains, they align, so they create a magnetic field. They create magnetic field. This would be North Pole, this would be South Pole. lines, they go from north to south. So that's what happens. Earth, planet Earth is also can be thought to be as a magnet. So if we have Earth, so we can imagine that there is a strong bare magnet inside planet Earth. So this would be geographic North Pole. This would be geographic South Pole. And this is if we imagine about magnetic field. So in geographic North Pole there is magnetic pole south. So lines, they go from N to S. The lines go from N to S. So this can be shown like this. So if you have compass, small compass arrow, so this arrow will be positioned, it shows north, because it is this north blue, it is aligned to the south pole. So south pole of a magnet of the Earth is in geographic North Pole, so differently, yes? What else? Now we said that electric current creates magnetic field. So either charge is moving with velocity v, or either in a wire the current is flowing. So these create B field, they together. This you have to remember. This definitely will be an exam, that moving charge particle or current, it creates B field. And if we have current, if we have a wire and the current is flowing in this wire, now how to determine the magnetic field direction? So we have current flowing from plus to minus. As you remember, electrons flow from minus to plus, but the current is flowing in opposite direction because it was historically defined. So for this we use the right hand rule, it's called. So right hand rule is would be like this. So imagine that this pen is a wire. So like this. Imagine that this pen is a wire. You take the wire and thumb is showing where the current is flowing. So current is flowing upside to the up, like this. And fingers, they show the direction of the magnetic field. So in this case, if I'm holding the wire like this, you don't need to hold the wire in practice. It's just just saying like that, and the current is flowing up. So thumb shows the direction of the wire, and fingers show the direction of the current of magnetic field. So magnetic field is going to this side, where my fingers are from left to right. So in front of me. So magnetic field would be shown like this, that it is flowing in this direction. So because like this. So if I'm showing on the fingers. So in this in front of the wire, it's flowing like this. Behind the wire, it's flowing like this, as the fingers show. So, and the closer to the wire, so around the wire there is magnetic field. Around wire there is magnetic field. So as closer to the wire, magnetic field is stronger. So this was the right hand rule. You do it with right hand. So right hand rule tells you the direction of B field of the wire carrying current. Basically, it's the current. It's what's the most important here. So it is what is the most important here. Now we can have you see, a wire produces magnetic field. So imagine if we turn this wire into a coil. So if we turn this wire into many times into coils, so like this, and we allow the current to flow, and we have here strong voltage supply. So because wire produces, because there's a current in the wire, and wire having current produces magnetic field, and when there are more wires close together, so there are circular coils, they are wound on a cylindrical form. So then magnetic field of these wires increases. So it gets stronger. So magnetic field of this bare magnet, it is, sorry, not of this solenoid. This is called solenoid. A lot of coils wound on a cylindrical form, and it creates magnetic field, and this magnetic field is similar to the magnetic field of a bare magnet. So of a bar magnet. So if current is flowing this way, this direction, so we can, according to the right hand rule, also we can determine that the lines are like this here. Inside the coil, the lines are like this. Outside the coil, the lines are in this direction. So if we have this so this is plus, this is minus, so it represents the magnetic field. I wanted to show you more nicer picture, but I failed to draw it nicely. So it represents, so the lines are like this, here the lines are different, so it represents the there should be 4 of them. Anyway, you will understand. So it represents the magnetic field of a bare magnet, and it's similar like we say, and it is stronger because of these coils that are here, because it's as increase the number of coils with each strength of the magnetic field. With each coil it adds up. So if you increase the number of coils twice, so then magnetic field strength increases twice. So magnetic field strength, I said, it's called magnetic induction. You can put the piece of iron here inside this, so the piece of iron gets magnetized by this magnetic field, and it also amplifies the magnetic field of these coils. So this is called the electromagnet. This thing, solenoid, which due to electric current turned into magnet. So this is called electromagnet. Now magnetic forces. Magnetic forces, objects interact due to magnetic forces. So magnetic forces. So if we have charged particle experiences the magnetic force, only if it moves perpendicularly to the magnetic field. Only if it moves perpendicularly to the magnetic field. So if we have I will try to draw a nicer picture. If we have S, and here we have N, so S and N parts of the magnet. So the magnetic field is going in this direction. It's going in this direction from N to S, and we have a particle that is coming here. Imagine it is positive particle. So this particle is coming here. It's moving with the velocity v. So experience magnetic only if it moves perpendicularly to the magnetic field. So magnetic field is orientated like this, and it moves like this. So they are orientated perpendicular. You see that this is up, this is down. So perpendicular, there's 90-degree angle would be between magnetic field. So magnetic field, external magnetic field, and velocity v, they have 90-degree angle. And the force that when it goes here, it's flying here, and the force that it experiences, it is in this direction, out. This is F magnetic. This magnetic force on charged particle is called Lorentz force. Magnetic force on charged particle is called Lorentz force. So in this case, on charged particle, if we have particles in mind, yeah, particle, and in this case we can use left hand rule for this. So it's very good representation in concept. So B direction is up, this V direction is here. Sorry, I forgot to show V. V direction is here. So it would be Z axis, Y axis, and F magnetic is in this axis. So this is a good representation. And also it can be shown by left hand rule. I don't know how I can show you. So left hand rule, if I have my left hand, so it means that I put it, so the lines of the B field have to come to my palm, like this. See, the lines are going to my palm. These fingers, all these fingers, except the thumb, they show the direction of particle velocity. They show the direction of particle velocity, and this thumb now, it shows the direction where magnetic force acts. So it's acting now in this case it's acting to me. So from the page to me, so in this direction, as you see, as I've drawn. So like this, where I'm speaking like now, from the page to me. So it is out of the page, we would say, out of the page. Now, so it is left hand rule. So only magnetic fields, only moving charged particle. Moving charged particle. Remember, moving charged particle, magnetic force. Moving charged particle. Now the same thing only with current. Current is also the flow of moving charged particles. So if we have where was that nice? If we have, again, if we have S and N, now we have magnetic field that is going the same, in the same direction, but in this case we have a wire with the current. So a wire with the current, in this we put here long wire, the current is going to which direction? The current is going from plus to minus, so the current is going to this direction. So imagine as a charged particle would going to this direction. Yes, so it means, again, we apply the left hand rule. So the magnetic field comes to my palm. This shows the direction of the current. Again, the velocity of a positive charged particle, because current is flowing from plus to minus. In current, electrons flow, but we can imagine that it is a flow of these pluses. It's just hypothetically in this case, and then this would show again the direction of the force that is acting on the wire, and this direction would be again out of the paper, the same as it was with Lorentz force, but in this case it is called this magnetic force which is acting on the wire. We all know that it's acting on the particles in the wire, on moving charged particles, but when we speak about wires, we call this magnetic force Ampere's force, because Ampere was first who quantified this interaction between wire and magnetic field, and Lorentz was the one who was who quantified the properties of moving particles in magnetic field. So this it's for them. So this is Ampere's force, and this is called Ampere's law, that magnetic field provides force on the current, so current carrying wire. So what else have I missed? So again, in this case, it would be the direction of the current, magnetic field, and this would be F magnetic, or in this case Ampere's force. So if you mix them, but it's not a big deal, but if you are true physicists, don't miss them if you speak with true physicists. Now this magnetic force that we're speaking about, magnetic force that, or charged particle or a wire in a magnetic field, it is, let's say it is the same, just the forces are called by different names. But this is used in electric motor. In electric motor, so electric motor. In electric motor, what do we have? We have, I will draw like this probably right now. We would have magnet that is, this is North Pole, this would be South Pole, and so lines are going from N to S. Again, it's okay, everything is okay. And now we have a loop of wire. How to draw this better right now? A loop of wire that is going and it's going back. So this would be a loop of wire. A loop, maybe not a loop, rectangular loop, let's say. So current is flowing from plus to minus. So current is flowing here in this direction from plus. Here current is flowing, and here current is coming back. So the direction of the current is different. So in this case, what's happening? Now, if I apply the left hand rule, so I would have to hold my hand like this. So these are going to my palm. These are going to my palm. This shows the direction of current fingers, and the magnetic field is coming to my palm. It means to this side, to this side of the palm of left hand. This shows the direction of the current, and now this shows the force. Direction of the force is down. So direction of the force, if it's down, so it means that I show it like this, that it is down. It's in the plane of the paper. In the plane of the paper. Yes, it would be like it's correct saying. So this is F magnetic, that is down, so it is amperes force. And in this case, because current is flowing in opposite direction, so this would be up. So this would be up. So amperes. So two forces acting on this. So it's turning. It's turning when when the position of this rectangular loop changes, then the forces change, but the forces, they always act so that they produce torque. So as you remember, torque was force times if we had rotational motion, we had axis, and one force was up, one force was down. So the torque would be this force and this length. Here the torque would be this length and the force, because these are equal forces. So the analysis simplifies. So it means that this rectangular loop is turned. This means, so there is a torque due to amperes force. So that's how electric motors work. Now so now we know that, what do we know now? That currents, electric currents, they produce electric current produces, or charged particle is the same, produces produces magnetic field. We know. So it means electric current, so it means moving charged particle, or particles, anyway, produces magnetic field. Now Faraday, scientist, a researcher, Michael Faraday, he in 19th century, the end of 19th century, he asked the question, can magnetic fields produce currents? If current produces magnetic field, so can magnetic field produce currents? So can magnetic field produce current? Faraday asked. So this was the question of Faraday. It seems that they can, if we have in this case a loop of wire, and we connect it to ampere meter, which measures current. So, and then how can it be done? How Faraday discovered it? We need he had bare magnet. Bare magnet has one N pole and south pole. So lines, they go from N to S. I'm showing this in different colors so that the loop wouldn't disappear from N to S. And it seems that the magnet has to move to produce electric current. So magnet has to move. Here moving charged particles create magnetic field. Here magnets have to move to create electric current. So to create electric current, it means at first it has to create voltage. So it means create voltage or electric field in the wire. So magnet has to move to produce electric current. So it means that magnetic field changing in time produces electric current, or basically saying produces electric field in the wire, and the electric field in the wire is E times delta L, and it is voltage. So magnetic field, if magnet is moving, then there is changing magnetic field that is crossing this coil, this loop, this magnetic loop, this loop of wire, closed loop of wire. So magnetic field is changing in time when you move it up or down. It's changing in time because the strength of magnetic field changes when you move it up or down, because here when magnetic field lines are closer together, it is stronger. Here it is weaker. So the strength of magnetic field changes in time, and it creates electric field in this wire. So and it is voltage, so current starts to flow in this wire. Now what's next? The next thing is that this is called electromagnetic induction. Electromagnetic induction it means that moving magnets, or basically electromagnetic induction, that magnetic field is used to create voltage, or if there is voltage, so there will be current. So used to create voltage. Magnetic field is used to create voltage, so changing magnetic field. Now there is when we have alternating current. So alternating current, we have a wire. And current is flowing. So it's flowing from plus to minus. So from plus to minus. So the direction of magnetic field would be from plus to minus, so would be in this direction. If the current is flowing like this, so it would be in this direction here. But when the polarity is reversed, then what happens? Then the direction of magnetic field changes and it goes to this direction. So if we have alternating current, the direction of magnetic field changes, and it means that it has to disappear. So it means that it disappears. So this, when we have this polarity, so there is magnetic field. When we just switch the poles, so this disappears and turns to other direction. So it means that it decreases, then it increases, because current is swinging like this in time. So it means that the polarity and also the strength of the current changes. So if this changes, so magnetic field strength, it also changes the strength and the polarity, because in order for this to change direction to this, it has to disappear, decrease to zero, and then from zero increase to some magnetic field value, but in this direction. So it means that when we have alternating current, so it produces naturally produces electromagnetic induction effect naturally. So transformers, there are devices called transformers. It is used to step up the voltage or to step down the voltage. So if we have, let's say, here only few coils of wire, and we have alternating voltage, so here we have a lot of coils in this, and imagine that there is a light bulb or something, and because there is alternating current flowing here, so here are less turns of the coils, and here are more turns of the coils. So when current flows in these coils, so it produces magnetic field, and because of the magnetic field, then magnetic field, it passes through these lines, and it creates voltage in these coils. So this is electromagnetic induction that is used in transformers. And what is interesting there is that this magnetic field, it can be amplified by ferromagnetic cord. So ferromagnetic cord of iron, it can be put in this, and it amplifies the amplifies the magnetic field. So this is like magnetic field of the solenoid. So we so imagine that this would be the magnetic field of a solenoid, and when this current flowing to this direction, so it current flowing to this direction, if it produces magnetic field. So when it is flowing to this direction, so it would produce the magnetic field that has the orientation like this. And so in one, let's say at one instant it will flow in this direction, at other instant it would flow in different direction, and this changing in the current flow, because current has to increase, then decrease, so magnetic field has to increase and decrease. So it means that magnetic field that is going across these loops is changing, and it is producing voltage, because there are more turns in this, more turns here, or more loops of wire than here. So then it means that voltage is increased. Voltage is increased. Of course, there is magnetic field that is going to this direction also, but here we are not concerned about it. Another thing that I want to show you is how electric generator works. Electric generator works on the principle that that if we have maybe like this, if we have again magnet poles, it would be south pole and it would be north pole. So magnetic field is going from north to south to this direction. This would be B field, and this B field, and we again, there would be a loop of wire here, a loop of wire, and when this loop of wire is connected, rectangular loop of wire is connected, it would be connected to some kind of light bulb, imagine. And if we were turning this, we would be turning this loop of wire, then what would happen? This loop of wire would be turning in a positive magnetic field, so it would be the same effect as magnetic field was changing. The same effect as magnetic field is changing. So it would be, this turning would produce voltage in the loop of wire. If we produce voltage, so then it means that the current starts to flow and the light bulb is up. So basically, what is what is important here, but if you notice, it's okay, but if you will not, it doesn't matter, that not only magnetic field may change, but can change the, if we have if we have a loop of wire, let's say a loop, this would be rectangular loop of wire, so it is moving in magnetic field. So in magnetic field, so there is called magnetic flux. Magnetic flux, and it is defined as magnetic induction times maybe we don't need these vectors, magnetic induction times the surface area times cosine alpha, that the angle between magnetic field lines and the plane of this rectangular loop. So any of this can change. So it means that magnetic field can change, area of this rectangular loop can change, so it can become smaller or weaker, and angle may change. So in this case, when we turn, we change the angle. Magnetic field is the same, but we turn the loop, we change this angle, alpha change, and because this changes, so changing magnetic flux creates voltage, or in this case, current. So this is more generalized thing that we were speaking. So not only magnetic fields may need to change to create voltage or current, but also also the surface area of the loop, or the angle may change. So all this is connected to magnetic flux. So changing magnetic flux, which incorporates magnetic field, surface area, and the angle. So now what I wanted to tell you, the last thing, it would be the summary of electromagnetism. Electromagnetism. So there are four, let's say, I would like to tell you four things, so that it is that electric charge creates electric field. You know this. Now magnetic magnets create magnetic field. So speaking about the first thing, I want to tell you that when we have positive electric charge, the electric field is going to this, like to infinity. So the lines of the electric field going to infinity. When we have bare magnet, the lines come back to this bare magnet. All the lines that go, they come back, but in the electric field, those lines that go, they don't come back. Remember this? This means that the lines of electric field diverge and these converge. These specific terms you don't need to know, but third thing is that changing magnetic field in time creates electric field. Creates electric field, and we can say that even add that changing magnetic flux, okay, changing magnetic flux, we can extend the first notion that we did earlier in this lecture. So changing magnetic flux creates electric field. So if it creates electric field, so in the wire, electric field in the wire, let's write maybe like this, creates electric field in the wire. So if electric field is created in the wire, then voltage, and according to Ohm's law, there is current. So this is electromagnetic induction. Yes, this is electromagnetic induction. Electromagnetic induction. Basically, the principle of electromagnetic induction. Now another thing, it is the fourth thing, it is that that currents or moving electric charges creates magnetic field. So this is Ampere's law. This previous was electromagnetic induction, or it was Faraday's law. Faraday's law. So Ampere's law. Now there was a scientist called James Clerk Maxwell, and he said, he added to this that currents or moving electric charge create magnetic field, but he added that changing in time electric field or changing electric flux, so it would be electric field times area times cosine alpha, the same as with magnetic field, produces magnetic field. So Maxwell said this last sentence. Maxwell said. So now what's happening? Changing, according to number 3, Faraday's law, changing magnetic field creates electric field. Changing B field creates E field. According to Maxwell, changing E field creates B field. And based on these two mathematically, very difficultly mathematically proven terms, he derived the equations of electromagnetic waves. So it means, he said, so there has to be electromagnetic waves where changing magnetic field creates electric field and changing electric field creates magnetic field. So of course changing magnetic field creates changing electric field, then changing electric field creates changing magnetic field. So we can draw this like this, and from this we go back to this. So it means that it is now continuous process, and Heinrich Hertz later he discovered electromagnetic waves, and these electromagnetic waves, they can travel in space at the speed of light. Speed of light is 3 times to the 8 meters per second. So these electromagnetic waves, they consist of changing magnetic field and electric field, and they travel at the speed of light. And we can show this as these are two perpendicular vectors. So if we have, this would be B field, this would be E field, so we would have like this, and we would have so magnetic field, and they oscillate and they travel in space at the speed of light. So this would be the direction of propagation. So it's called electromagnetic wave. Electromagnetic wave, you know, it travels at the speed of light. So all electromagnetic waves in space or in vacuum, 3 times to the 8 meters per second, so it's called speed of light. They travel at the speed of light. So there are various types of electromagnetic waves. Light, visible light is one of them. And how these electromagnetic waves are created, they can be created by antennas. So simply antenna would be if we have changing voltage, if we have alternating current, so then we would make some kind of circuit that looks like this, and this would be called the antenna. So changing voltage would produce plus charges here and minus charges here, and this would, and because current in the wire, it's going up or down, it's oscillating, so it is alternating current. And as you know, alternating current, it produces changing magnetic field. Alternating current produces magnetic field, then magnetic field produces electric field, and the electric field produced as magnetic, and again, and this is non-stop process, and this generates electromagnetic wave that travels. So this is called antenna. Basically, the antennas can be represented in this way, and this is electromagnetic wave. So alternating current creates magnetic field creates electric magnetic, and this is continuous process that is non-stop, and electromagnetic waves leave the antenna and travel through space at the speed of light. So we'll be dealing with electromagnetic waves in optics, and then we will a bit repeat these things and go on with the properties of light. So thank you.